from Cardiff, and he will talk on stability of the Calder problem for less regular conductivities.
All right. Yeah, so thank you very much. I wish to thank Malcolm Brown for inviting me to this great conference. Well, this is a joint work with Pedro Caro and Andoni Garcia from the University of Helsinki when I did my postdoc there. Now Andoni Garcia is working at University of Jyväskylä in Finland as well. All right, so well, Calderon problem is a very known problem in this conference, and, but let's recall once more a bit what's going on. So we consider the Dirichlet problem for the conductivity equation here, and we can assume a bounded domain in Rn, and gamma can be, let's assume it's L infinity, unbounded from below. So the Dirichlet to Neumann map corresponding to this conductivity gamma is the map mapping these Sobolev spaces on the boundary, defined this way for Fg in the Hilbertian Sobolev space H1 on the boundary, where U is an H1 solution in the interior to this problem 1, and V is any H1 function with trace G. So Calderon in the 80s, or as Samulis said maybe earlier, posed the question of if one can, if this lambda gamma determines uniquely gamma, first of all, and second, in the affirmative case, if there is a reconstruction algorithm to compute gamma from lambda gamma. All right. So well, this problem seems to require very different techniques in the plane or in dimension greater than 2. So I will focus on dimension greater than 2. So regarding uniqueness, injectivity means uniqueness means injectivity of the forward map. So several researchers have been studying this uniqueness issue for this interesting problem. The classical result by Sylvester and Ullmann for smooth conductivities on smooth domains. Adrian Nachman, who is in this room, gave a brilliant reconstruction algorithm, and in particular by product one gets uniqueness, assuming the conductivity in C11. And when several researchers have been working on this, and the best uniqueness result up to now is by Haberman and Tataru. In 2011 the paper was already uploaded in arXiv, assuming just C1 conductivities on a Lipschitz domain. I mean that the boundary is locally described by the graph of a Lipschitz function. Or they can assume as well that the conductivity is Lipschitz with an important constraint, that the gradient of the logarithm has to be small enough. So despite this problem is severely ill-posed, it's true that for certain Banach spaces one can find stability estimates. So it is known that if we measure the conductivities in the subnorm, the optimal modulus of continuity for the stability estimate has to be logarithmic. There is a paper by, I don't know how to pronounce, it's Mandache, in 2001, proving this optimality result. And the first result about internal stability for this problem, as far as I know, is by Giovanni Alessandrini. So in this paper, it is assumed that the conductivity a priori is lives in the Hilbertian Sobolev space with derivability exponent 2 plus s, with s greater than n halves, and the boundary is assumed to be smooth. So the best result previous to ours is by Heck, assuming the conductivity in these Calder type spaces C1 1 plus 1/2 plus epsilon, and assuming as well that the conductivity is in this Sobolev space. So what we have done is rewriting the classical stability proof by Alessandrini in this approach by Haberman and Tataru, using the idea of decay in average of the potentials. We use, as Sylvester and Ullman did, the Schrödinger equation approach. So what we get is to decrease the assumed regularity a priori for the conductivity from C1 1/2 plus epsilon to C1 epsilon. So this is our theorem. So we consider our admissible coefficients to be in the class C1 epsilon, bounded from below and from above in the C1 epsilon norm. So in this case, so we get this logarithmic type stability in H1 norm. By argument of interpolation and Moray embedding, we can get also a stability in the Calder norm. Since this norm is stronger, that the H1, the exponent is a bit worse. I can show you this argument. So we know that if we have a stability in H1 norm, and we have a priori bounds in the Calder, in this Calder space C1 epsilon, this C1 epsilon is a stronger space than W1 infinity, this Sobolev space. So you can interpolate. We consider delta between 0 and 1, and then we get estimates in the norm n over 1 minus delta by interpolation, and by Moray embedding you have estimates in the Calder class. So, well, first of all, here I show you an estimate relating interior information in the interior and on the boundary for the solutions to the Schrödinger equation. Maybe it's worthy here to clarify a bit the setting. So if we consider conductivities gamma j let's say Lipschitz in Rn, we always will assume that these conductivities take one outside a ball, and they are bounded from below by a positive constant. So we will call Uj the H1 log solution, weak solution to the conductivity equation with coefficient gamma j, and but rescaling operation, if we define Vj as gamma j power to 1/2 times Uj, then this is a weak solution to the Schrödinger type equation, where here the potential is defined like this. So it has to be defined in the weak form. It's not a function anymore, of course. It lives in a Sobolev space with negative exponent. This is a bit the questions we are dealing with, and what this identity says is the result of acting Q1 minus Q2 on the product of solutions V1, V2 can be bounded for this expression. So we here need to perform extensions of our coefficients gamma 1, gamma 2 in such a way that we need to control this term in particular. So it's important to control this term in terms of information at the boundary of omega, because then we use another Alessandrini stability result at the boundary. So the Whitney type extensions are fabulous for this. Right. So our extensions preserve the C1 epsilon regularity, the boundedness from below. They take one outside the ball, containing the closure or the topological closure of omega, and they have this important condition for our purposes. Right. All right. So, the CGO solutions used in Haberman and Tataru's paper are the same as Sylvester and Ullman. These exponentially growing solutions. So, where this exponential means exponential of zeta times x. This zeta is a complex vector parameter such that zeta times zeta is 0. This means that the real and the imaginary parts of zeta are orthogonal each other and of the same Euclidean norm. And the idea is that these solutions, or the residual, have to tend to 0 in some sense when the modulus of zeta tends to infinity. And it is easy to check that a solution U, H1 log, of the generalized Laplacian or Laplace equation, as I explained a bit here. U is solution to this if and only if the V rescaled like this is a solution to the Schrödinger type equation. At the same time, this solution V is of this type. Solves the Schrödinger equation if and only if the residual solves this another second order equation. Here appears an operator, differential operator, minus Laplacian minus 2 zeta times gradient, that can be called the conjugated Laplacian, because it's nothing but conjugating the exponentials with the Laplacian. Also, it's called the Faddeev operator. And they introduce these Bourgain's spaces. So the homogeneous Bourgain space is given by this norm, the tempered distributions, such that this amount is finite. This would be the homogeneous space, and this the non-homogeneous space, where this p zeta is the symbol of this conjugated Laplacian operator. And I would say that these are the natural spaces to deal with this Faddeev operator, because the inverse in the operator norm of the inverse in these spaces is 1. So this is very, very nice. Because in other papers, Sylvester Ullmann, Russell Brown, they tried to get a decay for this norm in LP spaces, L2 weighted spaces, and so on. But with these spaces, we don't need decay here. The norm is 1, and what one needs to apply the Neumann series theorem is to check that the norm of the multiplication operator by Q is less than 1. Well, these are the weak solutions of the weak definitions of the potential and the multiplication operator by Q. So the idea is that we can express the residual in terms of the potential as far as the norm of MQ is less than 1 in these spaces, operator norm. So if we get decay for this term, automatically we get decay for the residual. So, well, the proof is quite technical, but let me say that if we consider Lipschitz conductivity, then Habermas and Tataru are able to prove that the norm of MQ is bounded modulus multiplicative constant by this guy. So, of course, to guarantee that this is that the norm of MQ is less than 1, the gradient of the logarithm has to be small enough. In turn, if gamma is assumed to be C1, then doing some computations, one can get this estimate, where here we have decay in zeta, we have decay in zeta, and the modulus of continuity, the modulus, the L infinity modulus of continuity for the first order derivatives of the logarithm appears. So since these gammas are constant outside the ball, then and these derivatives are assumed to be continuous, So they are uniformly continuous, and this term goes to 0 when modulus of zeta grows. Then for zeta large enough, we have that the norm of MQ is less than 1 here. So C1 is a natural here regularity needed principle. So it seems that it's not possible to get directly decay for the norm of the potential in modulus of zeta. So what the authors do is to get decay in average. So let's see. Let me show this idea. So doing some computations, one can estimate the norm of the potential in the suitable space by this. So here the bad term is this Laplacian. This phi appears, it's a smooth function compactly supported that takes one on a ball. This is a bit technical. There are some localization estimates taking the most that the potential is compactly supported, and well. But the fact is that in this term is not, in principle, it seems not possible to get decay in modulus of zeta. So in order to deal with this animal, Haberman and Tataru propose this decay in average. So let's have a look to this idea. So, well, we fix here k. It will be a frequency variable. So, in principle, the idea here, I don't know if we can. We have here k in Rn. So we consider P a two-dimensional subspace, linear subspace, orthogonal to K. This is possible in dimension greater than or equal to 3. And what we do is to choose eta in the unit sphere intersection with this plane, and another unitary vector kappa such that eta kappa becomes a positively oriented orthonormal basis of P. So with these choices, then you consider one real number S, positive real number S, less than modulus of K over 2. And the composition became standard after Sylvester-Ullmann paper, and this is the choice of zeta, of the parameter zeta. So all these properties are hold, and the idea is that the function of zeta you wish to average, you have to integrate it in this manifold, lambda to lambda times S, where S is this circumference or manifold, and we integrate this with respect to this measure, and this way the average is taken. All right. So for this Laplacian term, we play with a modifier, an approximation to the identity, and after doing some computations, one can get this expression here. So if you want only uniqueness, in principle C1 is C1 conductivity, C1 regularity is enough, but if you want a stability, you need here to control this L2 modulus of continuity by positive power of epsilon, and this is where we require that the first order derivatives of the logarithm of gamma has to lie in the Bezoff space to infinity epsilon. But it's possible. You get estimates, and this is the idea. Then, if we consider the whole picture, we have that this term is bounded by this expression. And then we take this h coming from the modifier like this to balance terms, and we can get this time. And this is the key of the proof. This is the novelty. And then it's a matter of rewriting this Alessandrini's argument. All right. So it turns out that this difference solves this elliptic problem, and this allows to control the H1 norm of the conductivities in terms of the H-1 norm of the difference of the potentials, the well-posedness of this elliptic problem. So we consider here the definition of the H-1 norm in terms of the Fourier transform, and we fix a constant t greater than 1 in order to split the integral expression between low frequencies and high frequencies. So to deal with the high frequencies, we don't have to make a great effort, because we can, in a way, take the most of the decay of this term here for high frequencies. So again, the Laplacian term here is the difficult guy. So we use again this modifier, and we end up again with the L2 modulus of continuity of the first order derivatives of the logarithm. All right. So this extra of regularity, we need this epsilon, C1 epsilon, to get the estimate. So, well, there are a lot of details here, but now we choose H like this, and we can bound this bad term with the Laplacian by this. And well, at the end, you end up with this estimate for the H-1 norm of the difference of the potentials. Right. So here, what we have to do is to find a uniform bound for the Fourier transform of Q1 minus Q2 in K for modulus of K less than T. And well, here we consider, we apply that we have here a compactly supported distribution. Therefore, its Fourier transform in one point can be expressed like this. So we have a clever, we use a clever choice of these zetas in such a way that zeta 1 plus zeta 2 is ik, and u zeta j are the solutions to the corresponding Schrödinger equations. All right, so then here we apply Q1 minus Q2 to the product of the solutions, V1, V2, and we get this expression here. So if you want to bound the Fourier transform, you can do it in terms of the other terms showing here. So well, we apply all the machinery we have seen here. We use the boundary interior estimate. Some computations has to be done here to estimate these guys. We use stability at the boundary by Alessandrini, and you end up with this kind of expression here. We can bound the residuals by the potentials, and we have this expression. We use here that, of course, the H1 solutions on the ball of the H1 norm of the solutions are have this exponential behavior. And then what we do is to apply average to this estimate. So the left-hand side does not depend on zeta, so it will remain unchanged. And well, we have this when we apply this decay in average. All right. So we end up with this expression, and then well, you have to choose the correct parameters in order to get the desired result. But it's quite technical, this. So I end here.
Okay, in which form can you state the sharpness of the estimates which you have obtained with this omega?
The sharpness.
Yeah.
Well, what we know is that we cannot obtain a quicker modulus of continuity than logarithmic. This is for sure, because for this argument here, if you measure the outputs in H1, then necessarily you have the conductivities controlled in this Calder norm. So, in particular, in L infinity. So.
I don't understand this, but have you some counter examples, whatever?
Yeah, well, no, it is known that this logarithmic modulus of continuity is optimal. Is optimal, yeah. If you measure, if in the left-hand side you have is this the subnorm. in this case, this is known that omega cannot be quicker than the logarithmic type.
And there is an example in that paper that you cited, is there, that shows that?
They show this, yeah, this in Mandache 2001. Yeah. There is also a classical example here by Alessandrini showing that it's not possible that omega is the identity. So there is no Lipschitz also.
Then let's thank the speaker again.
Thank you.